Practice problem 9-E4. Force first position graph, 32 modified. Figure 7.16. Okay, so this is a Unit 8 practice problem here, and we're going to take it a little bit further than we took the original example with the Slinky Dog. What we have here is a force position graph, or a force displacement graph of some object. I don't know what the object is, quite frankly. It doesn't matter. But what we know is that the object has a mass of 1.7 kilograms, because we're just given that. And we know at this initial position, 0.25 meters. So right about here on the graph. We know that at that point, the initial speed of the object is 0.44 meters per second. What we would like to do here is we want to figure out what is the speed of the object whenever it reaches 1 meter all the way out to the edge. So what is that final speed? Well, normally if we were looking at speeds in this way, and we were looking at distances or displacements like this, we would think that we'd want to use the work equals a change of kinetic energy. That's our work energy theorem. And if we blew that equation out, we normally write it as like F delta X. There's a cosine theta in there because it's a dot product. And this would equal 1/2 m times Vf squared minus Vi squared. But if we use this equation right now, there's a little bit of an issue. I have no idea what this force is, because this force starts here at 0.8, and then it goes to 0.4, and then it goes to 0.2. It changes repeatedly. What's actually going to be a nicer thing for us to do here is to remember that this entire F delta X cosine theta, that is equal to the work. And we also know that on a force position graph, that amount of work is nothing more than the area underneath this function, from our initial position to our final position. So if we could find this amount of area will be this entire fx cosine theta term. And then we could go ahead and solve this problem, because we'll know the initial velocity, we'll know the mass, we'll know whatever this number is over here, and we can solve for the final. So let's go ahead here and try to figure out what is this area that I've kind of checkered in red over here. Now, if you want, you can pause this, try to figure out this area on your own. There's many different ways to do it, whatever floats your boat. And then when we unpause, we'll try to figure out what that area is together. Okay, so if you wanted to, there's a few different ways you can find areas of this. Some people like to make horizontal lines like this, so they have 3 different rectangles. Personally, on this one, I like to make vertical lines like this. So I have 3 rectangles, rectangle 1, rectangle 2, and rectangle 3. Note that we're not actually finding the area of this over here. Our initial position was at 0.25, so we're going from that to the right. That's what we actually care about. It so happens here that every baseline is 0.25, so all of these are 0.25 here. And then we just need to multiply that by the height of all of these. And as we see, we've got a 0.8, so 0.25 or a quarter or of 0.8 is just going to be 0.2. For here, we have 0.25 times 0.4, so a quarter of 0.4 is 0.1, so we're at 0.3 total right now, plus the end. And then for our last one, 0.25 of 2 gives us, or of 0.2 rather, gives us 0.05. So we add 0.2 and 0.1 and 0.05 together, our total area should be 0.35. That's our total area when we add them all up. And that's going to be in joules, because that's what the work is. The work is some amount of energy. And then we can say this is equal to 1/2 times the mass of 1.7 kilograms, multiplied by some unknown final velocity, that's what we're looking for, minus the initial velocity, which we had of 0.44 squared. And looking at this, this now gives the impression of a problem we've already done. We have already done in our work energy section of this unit problems that look just like this, where we're trying to find some final velocity. The only thing that makes this one just a little bit harder is the fact that this 1/2 times 1.7, that value is technically going to be distributed to both the VF squared and the 0.44 squared. And that's something we need to be very, very careful about. A slightly easier way to get rid of it, though, instead of having to distribute to both of them, is instead of distributing it, let's put the 1/2 and 1.7 together now and just write it all out again. So we've got the 0.35 equals, well, 1/2 of 1.7 is 0.85. And then we've got VF squared minus 0.44 squared. What this allows us to do is, instead of distributing this 0.85 over, we could divide by the 0.85 now. And that way, this problem looks a little bit neater. Dividing 0.35 by 0.85 gives us on the left-hand side here 0.41 equals, and then we have VF squared minus, and then let's square the 0.44 right now. So 0.44 squared, we're going to get a smaller number because we're multiplying a decimal by a decimal. So this is just going to be 0.19. That's what this became. And now this is actually pretty straightforward for us to solve. We could add 0.19 to each side to wipe this. On our left side here, we're now just going to have 0.60. This is going to equal VF squared. And then we're familiar with, if we want to get rid of the square, we take the square root. So we can just say that our final velocity here is the square root of 0.6. And if we take the square root of 0.6, we get 0.77. Naturally, our units are in meters per second because we're looking for a speed here. So pretty much the only new thing we did in this problem was we had to find the areas of 3 rectangles and add them together, which that really isn't new. We've been able to find areas of rectangles for years now. We've been able to add numbers together for a decade or so, since like first grade. And at that point, it just went back to an old problem we did with a little bit of algebra. So with that, this problem is finished. We're going to do another practice example like this in another video. Similar idea with work energies and finding areas. But until next time, hope you enjoyed this one, and adios. Take it easy.